I've now asked Yanbei to come in and tell us all of the things that we're doing wrong, all of the things that we're missing, that we should be concentrating on but aren't doing.
I think, so in my talk, the title of my talk will be Quantum Metrology and Gravitational Wave Detectors. It really simplifies gravitational wave detection into a very simple system and talk about the quantum mechanical aspect of it. I think the motivation for doing this is partly because maybe in the future this could help improve gravitational wave detection. And the other thing is that there are other communities in physics which are working on quantum metrology, which means you're making an experiment where your sensitivity is currently or maybe in the future limited by quantum uncertainties. And this is a subject which is related to the new technologies. And then the other hope would be that what we do here or what we do here in gravitational wave community may benefit other fields, not only in the form of coming up with strategies that they may use for other experiments, but also motivating the other communities to improve their technology so that one day maybe they will be applicable to gravitational wave detection. Okay, so talking about quantum mechanics, there are in the past decades, people have thought of two ways that quantum mechanics can limit the sensitivity of gravitational wave detectors. The first one, I think we're more familiar about, which is the so-called standard quantum limit. So this is basically arising from the Heisenberg uncertainty when you're using test masses and light to measure gravitational waves. If you measure the position of these test masses a lot more, you will have to perturb the momentum of the test masses, and this causes the back action noise. And in terms of LIGO, this will be the radiation pressure noise. And Rana mentioned this is very hard to measure, but you see, if you do measure the radiation pressure noise, you're basically witnessing these 40 kilogram objects obeying the Heisenberg uncertainty principle. So I think that's on its own is a very interesting fundamental physics effect. So then if you look into the future, if you are getting rid of all the technical noises, and if you raise the laser power, or if you use squeeze vacuum injection, then the so-called standard quantum limit may come in and limit your sensitivity. And to go around this, you need to build correlations between the test mass and the light in the interferometer. I'll mention a little more, but let me talk more about this other limit, which is the so-called energetic quantum limit, as being called by Brzezinski and Khalili. And basically here it says if we apply another kind of uncertainty principle, the energy phase uncertainty principle, to the light field, which is in the interferometer, we will see that you also use the formalism of so-called quantum Fisher information. You obtain another limit which says that your sensitivity is going to be limited by the energy content in the interferometer. Here, I assume the wavelength of your gravitational wave is much longer than the size of the detector, which is generally true for ground-based detectors. So you see here that it is the energy content. So basically, it doesn't matter how long or how short the arm is, and how high, how low the finesse of the interferometer. It's basically the total energy you have, or the quantum fluctuation in the amount of energy you have in the cavity that matters. So it turns out this is just related to the amount of shot noise. But I think as we say a little more, it'll be a little more rich than just shot noise. So basically the energetic quantum limit is what you are limited by if you get rid of the radiation pressure noise. Okay, so here I mentioned there are approaches. So this is how the standard quantum limit shows up. And there I mentioned a little bit of how you go around the standard quantum limit. So here, as a theory talk, I just have the dimensionless units. Basically, if you have a gravitational wave detector which measures position, at high frequencies, you'll be limited by shot noise. But then at low frequencies, you will be limited by the radiation pressure noise, which is the quantum backaction. If you increase the amount of power, you will be lowering the shot noise, but then you have higher radiation pressure noise. And vice versa, if you lower the power, you have lower radiation pressure noise or backaction noise, but you have higher shot noise. So at the end, you'll be limited by this curve, the so-called standard quantum limit, which, if you compare this with the advanced LIGO current sensitivity, we're a factor of 2 away from it. So there are various techniques that people have developed, some of them tested to improve the detector sensitivity beyond the standard quantum limit. For example, injecting squeezed vacuum or entangled states, or detection of the frequency-dependent quadratures, or the modifying optical transfer functions, or the test mass dynamics. I wouldn't go into many details, but to say that some of these, for example, the injection of squeezed vacuum is already planned for the A+ upgrade. But let me turn to the more interesting, I think, the energetic quantum limit, which basically says that it's actually very simple. If you take the energetic limit and then you take 1 over the SH and you integrate over all the frequencies, you'll find that the integral of 1 over the noise spectrum over all frequencies is limited by the energy uncertainty, the total energy uncertainty in the arm cavity divided by h bar squared. Okay, so that basically says, also if you have a coherent quantum state, energy uncertainty is related, the variance of energy is energy squared divided by photon number. So at the end, given the same total energy in the arm, you will be able to have the same integrated sensitivity here. So what is the meaning of this integral of 1 over SH? It'll be the SNR for a burst source. It's also, if you look at the spectrum in the plot, it's basically, if you have the 1 over SH integral the same, it means that if you have a more narrowband detector, you will be able to improve your peak sensitivity, but your bandwidth is limited. But if you decrease the finesse of your cavity, you'll have a broader bandwidth, but you have a worse peak sensitivity. The product of the bandwidth and the peak sensitivity will be the same. So this was already realized by Jun Mizuno in the 90s when he was thinking about signal recycling versus resonant sideband extraction. So I think when the time for the cosmic explorer, especially when we have 40 kilometers, we actually have such an issue because this bandwidth have to do with how long the light travels in the arms and then how many times the light is stored. So if we have cosmic explorer, which is 40 kilometers, if we store the light, if we allow the high finesse in the arm cavity, we will severely limit our bandwidth. And then from this bandwidth sensitivity limit, it actually means that for a long interferometer, we may come toward this limit more severely than advanced LIGO, for example. So historically, people have thought about how do we circumvent this bandwidth sensitivity limit. So they came up with this very nice idea, which I will say that this may not be the right way to think about it, but this is how they came up with this. They said, you know, if you have the arm cavity, the reason why the arm cavity has a finite bandwidth is that because the signal travels from one side of the arm and to the other side and comes back, there is a time delay and there is a phase shift, which is proportional to the distance from the one side of the round trip, right? There's a distance. So what if we're able to build an anomalous dispersion in such a way that the propagation phase shift is 2 omega L over C, but our anomalous phase shift would exactly cancel the propagation phase shift. Therefore, the light would go around in the cavity as many times as they want, but there is no phase shift. and therefore our bandwidth is very broad and our gain is very high. So this sounds so great. So over the past many years, starting from the 90s, people have thought about how to make this. But one problem that we thought, which is a little bit weird, is that if you're able to have an anomalous phase shift, what it means is that if you have a wave packet that tries to go into this anomalous medium, because your partial phi, partial omega is negative, it means that your wave packet would come out from the medium before it comes in. Okay, so it doesn't violate, okay, it looks as if it violates causality, but in principle, if you have a signal which is limited in bandwidth, you could have such a response. Okay, but that point was a little bit confusing for a lot of us, and over the many years, we doubted whether this is even possible. But a few years ago, Haixing Miao came up with this very interesting idea. He said that if you have an unstable optomechanical system, it turns out a feature of an unstable system would be that the outgoing field coming back actually has a phase shift, which is not a phase lag, but a phase advance. So this is a well-known effect in engineering. You can apply this to quantum measurement scenarios, and then what you find out is that you can actually construct a system which is made up from, made up from an unstable mechanical oscillator coupled with a LIGO-like interferometer, and then have a situation where this anomalous phase shift would allow you to cancel the delay in the arms, and then have an effect which basically has an improved bandwidth without sacrificing sensitivity. And Haixing and Juan and Dennis Martinov tried some ideas of attaching some optomechanical amplifiers into this system and try to say that, okay, maybe you can have some configurations where you can improve the bandwidth of LIGO detectors. Okay, so these schemes may not be practical, but it shows that in principle we can use this kind of unstable systems which have parametric amplifications built in to have improvement of sensitivity. So there's also more recent work. We have shown that, in fact, you don't have to have this instability or unstable systems. In general, the reason why these systems are able to broaden the bandwidth and improve the product of sensitivity and bandwidth is because they have amplification processes built in. So let me try to then make some connections to the more broader context of what people are thinking about in the quantum metrology community. Okay, so let me show this diagram. And then it turns out in this diagram, different aspects of this diagram can be connected to what the quantum metrology community are thinking about. So in this diagram, I'm showing a gravitational wave detector as a bunch of oscillators which are coupled to each other with different kinds of Hamiltonian. Okay, so this is the arm cavity of the LIGO detector, let's say, and this is the test mass, the mirrors, and this is gravitational wave coupling with the arm, and then the arm cavity mode coupled with the mirror motion. So these two things together is Fabry-Perot-Michelson interferometer. And then if you couple this A to another mode with this coupling, so this will be realizable by just two cavities, one arm cavity, another additional cavity, you couple with them like this. So this turns out to be the so-called speed meter configuration. And then you can couple that additional mode to a mechanical oscillator through this parametric amplification Hamiltonian, okay? As it turns out, if you do this, what you're having is this white light cavity interferometer that Haixing has come up with. So if you look at this already, this kind of thing, what we're doing is, we're attaching different things to LIGO, but one way to think about it is that we're doing a coherent quantum feedback system. Okay, so what does that mean? It means that we're taking the outgoing field from the LIGO interferometer and we're processing it with a coherent quantum mechanical system and then feeding it back. So there are some discussions of these kind of systems in the community, and people usually say that, oh, this coherent quantum feedback may help detector sensitivity. And then, so the other discussion that some people have made is that they show that quantum error correction, which is also a kind of feedback, may be used for improving detector sensitivity. So I think this kind of diagram where attaching stuff to the main LIGO interferometer can be viewed in this broader context. Okay, so let me continue. So now we have attached this mechanical oscillator to this mode, and what if we attach another hypothetical object which mathematically has a negative mass? So if we do that, then what we have constructed is a system that has a PT symmetry. Okay, so what does it mean, a PT symmetry? P is parity and T is time reversal. So this so-called PT symmetry has nothing to do with the fundamental physics, PT symmetry, but it has to do with the fact that if you take this B and B dagger as the center of your picture, things on the left and things on the right are basically time reversed, because here I have B dagger and A coupled, but here B is coupled to C dagger. Okay, whenever you put a dagger, you're doing time reversal. And since here I have a positive mass, I have a negative mass, so I have time reversal. So people have been saying that systems with PT symmetry may be very good at enhancing detection sensitivity. So this can embody itself, this kind of principle. If we make it here, it'll basically result in such a system, which is even an extension to Hsiing's so-called white light cavity configuration. So, and then it turns out, if you take this kind of system, the effect of back action on the positive mass would actually cancel the effective back action on the negative mass. And this results in the so-called quantum mechanics free measuring device that Carl Caves has been proposing. And finally, if we view, broadly speaking, we have a bunch of oscillators that are coupled with different Hamiltonian, and this is maybe a good starting point for optimizing these kind of systems for gravitational wave detection in a more systematic way. So these are a lot of buzzwords, but I think the point is that by making these connections, we can use gravitational wave detection to motivate the broader quantum metrology community. Well, let me finally go to the final slide. I think some of them you might noticed that Rana has changed his name from Rana Adhikari to Rana X Adhikari. So this may be the X here. So here, let me just mention what he wanted me to also show is that not only, so in the gravitational wave community, we have studied a lot of experimental techniques, theoretical strategies. We can also think, what kind of other applications we can apply gravitational wave techniques to measuring other systems. We have optimized our coupling to gravitational waves, and what about these axion and other more novel kinds of fields which may be coupled to novel kind of excitations in our measuring devices. So let me just stop here. Thank you.
Thanks very much, Yanbei. I'm going to take the chair's prerogative and ask the first question, which is, how long should we make the arms for your quantum mechanics free interferometer?
Oh, I don't know.
That's a joke. That's a joke.
Okay, I think it could be as long as you want.
Okay, I think it's really great to see some of these new ideas coming in and hopefully disrupting things so we don't just fall into the trap of continuing to do the same things we did before, only better. Now, let's get a real question. Sathya?
It's really along the same lines. Does it mean detectors are not, I don't think you mean we will not be limited by quantum mechanics. I don't.
No.
Does it really mean quantum mechanics free in the sense we don't have to worry about quantum noise? What exactly does that phrase
why
mean?
it's a buzzword.
Yeah.
Which is not a lie. Maybe it's a lie, but it's a way to make people get their attention. Quantum mechanics free means that, I think what Carl Caves means is that there are subsystems inside the system where within the system, the degrees of freedom only respond to the signal you try to detect, but doesn't necessarily respond to any external quantum fluctuations that drive the system. But then when you actually try to detect the signal, your system will no longer be free from quantum mechanics, and it'll be subject to the shot noise you will have. So my understanding is that this quantum mechanics free means that you're evading back action. So the device will not have radiation pressure noise.
Yeah.
It only has the shot noise.
Okay, but that's the quantum mechanical noise.
I think so. I think so.
So just two quick questions. One is that how do you in practice implement a system with negative mass? Because to get the PT symmetry, the other system, mechanical system that you're coupling, somehow must mimic negative mass feature. So how do you in practice couple that? And second question is, since in between you have to have coherent quantum feedback system, does it mean that you have to keep it at sufficiently low temperature so that there's no decoherence, which will spoil the quantum phase to be there, not get destroyed?
Okay, so let me answer the first question. Negative mass is a mathematical construction. You need to realize a Hamiltonian that corresponds to the negative mass. I think existing in the literature, there are two ways. I think when Carl Caves first thought of this, he constructed some coupled optical parametric amplifiers and cavities that together realize such a negative mass. It looks very complex, but it is used to illustrate his idea. And then also Farid Khalili and Eugene Potzik, they propose that there are atomic systems where if you do the right pumping, it may also exhibit negative mass. I feel like both systems may not be very practical for gravitational wave detectors. So there should be more thinking to actually try to realize such a system. So maybe you don't necessarily have to realize the negative mass on its own. Maybe you can try to find a system that realizes the combination of the mechanical oscillator and the mass. But indeed, there's no very simple realization of such a thing yet. And the other question about to be coherent, is it necessary to be free from decoherence? And that's totally true. So in here, if you have, so these are just some balls which are mathematical. But if you try to realize this using optical modes, then decoherence usually means losses to the environment. So you must have system with low optical losses, including you have to match the modes of these modes very well. So usually the matching the modes the optical decoherence may be less of an issue than if you have mechanical oscillators here. Because for mechanical oscillators, you must make sure that their thermal noise doesn't contaminate your quantum coherence. So both are very important issues. So for mechanical oscillators, you will have to keep them at low temperature, and they have to have very high quality factor. So maintain, you have to, but in principle, I think people think that maybe for optics, it's easier to have higher coherence within the interferometer than at the detector, because sometimes the photodetector's quantum efficiency, when it's not one, it also creates decoherence. So I think a lot of people say that maybe it's better to have an amplified signal within your quantum system, within your coherent quantum feedback system, than injecting squeeze vacuum and then try to improve your sensitivity.
I'd like to open it up and sort of take questions for anyone from, for any of the speakers today, but you had your...
Is it this negative mass responsible for the PT symmetry? The negative mass in this system, is it that responsible for the PT symmetry? Because the understanding that I have is that it is the balanced gain and loss.
Yes.
Some of the gain and loss has to be balanced in order to have the proper PT symmetry. So
yes. So usually when people talk about the PT symmetry, they don't have a moving test mass in their system. Usually people talk about two simple oscillators that are just time reversal to each other, and you couple to a main mode here. So in that way, you don't need any negative mass. You already have PT symmetry when you have the A and B and C. But if you want to include the mass into your PT symmetry, then I think you will need a negative mass. So that basically the things on the left side of B have one kind of response, and the things on the right side of B have another kind, and then at the end they cancel each other, and then you have a very good gain in sensitivity over all frequencies.
okay.
Yeah.
Sanjit?
Simple question. Are these theoretical ideas, or people have actually tested the negative mass and the anomalous phase?
I think they can do some tabletop test in atomic systems, maybe. I don't know whether Eugene Posick did that. Ian Farid wrote a theoretical paper. I think the problem with implementing this in LIGO is that you not only have to test it in the transfer functions, you also have to make a very low noise measurements. That is very challenging. But I think if you just say, let's forget about the negative and positive mass, let's just talk about the arm cavity versus this oscillator. That particular PT symmetry system, I think, were studied experimentally by people at UWA, but they simply showed the transfer function is broadened. Also, there are experiments at Northwestern, but all of them are basically showing that the bandwidth is broadened. They may not have shown that noise is actually lowered. Yeah.
Okay. Other questions? Yes.
Yeah, so you had an H coming from the GW part, which is coupled to a A1, this minus alpha A1H.
Yes.
So is H an operator?
Is what?
Operator? In
Yes,
the
yes. All of these are operators.
So how are you operatorizing the GW part? Like we do not know.
So here, what I'm coupling is the stress energy tensor of your system to the gravitational wave. And then the stress part of the gravitational wave is coming from the device is coming from the electromagnetic mode. And then therefore it is the amplitude modulation in the arm that is coupled to gravitational wave. So therefore amplitude modulation is this A1 quadrature. So that's why A1 times H is the interaction Hamiltonian.
E1 part I understand. I'm just asking how you are writing H. Because that would require you some knowledge about quantum nature of gravity or something. Because how can you write operatorize the, gravitational wave?
So H is not an operator here. H is a scalar. Sorry. H here is a number, not an operator.
So A1 is just the only operator here.
A1 is the only operator.
Okay,
Yes.
but then is it Hermitian?
A1 is a quadrature operator. So A1 is Hermitian.
Okay.
But these are not Hermitian. These are just a shorthand for this one has to plus the Hermitian conjugate.
Okay, so A1 is Hermitian.
So here A1 is Hermitian.
Oh,
Yes.
thank you.
Yes.
Sir?
I have a question for the other members of the panel. So,
Okay.
Yo mentioned that we need, was it Yo? I think it was Yo who mentioned that we need a kind of global collaboration going forward in order to pool our resources and come together to divide the very challenging task of investing in technology for future detectors. I would like to know what efforts are underway to form such a collaborative effort.
Yo, would you like to comment on that? What efforts are underway or what's missing?
There are some discussions going on in the context of GRIC, the Gravitational International Committee. But the question is how to really implement it. And my favor would be to do an adiabatic implementation where you first start building a global community, and you start informing people of what is going on. So instead of immediately trying to discuss things like funding and things like that, that could happen in a later stage. So these initial discussions are going on. I personally believe that it will be best to start from the existing collaborations, so that, for example, LIGO, Virgo, Kagra, LIGO India would start doing that, and then start coordinating what would be most useful, for example, in R&D, instead of making something new and abstract.
Under the Gravitational Wave International Committee, the committee which is set up for 3G developments and looking at the future, there is a plan that we should perhaps form a committee will keep that 3G committee going to set up a number of meetings over the next year or so on the different major subsystems to bring together a community to start discussing how we go from where we are now to where we want to be, that we involve another committee called the GWAC, which is the Gravitational Wave Agency Correspondence, which gets the funding agency people together, and they want to integrate or be involved with the R&D type developments. So we can start to try and find ways that globally the national R&D research agencies can support global efforts.
I would like to add that in this particular effort, I think India is in a special position where we are building our facilities, and we plan to invest in a large way in across the Indian community in research. And I think it would be a great idea if we could be part of this roadmap.
As far as regarding the GWAC, there should be. It's open to all funding agencies that are interested in gravitational waves. I think it doesn't, if I remember right, it doesn't currently have an Indian representative attending the meetings. Sorry? Okay, good. So that's the first step there. On the 3G developments, we tried to include some people from India in the R&D side. One of the issues, of course, that happens there is finding a time which people around the world are happy to meet at.
One of the issues with GWAC and Indian participation is that the Indian method of funding large science has really the funding agency and the implementing agency are both the same entity, DAE. And so the correspondence in the US, for example, LIGO is a part of GWIC, but the NSF, which funds LIGO, is a part of GWAC. And that relationship mirrors a similar organization in the high energy physics community called the International ILC, the International Linear Collider Collaboration, and then there was something called FALC, the funding agencies for a linear collider, which again had the projects on having one organization, FALC having a similar organization, and those two organizations had adjacent meetings. For example, the ILC would have a meeting, and then the FALC would have a meeting the day afterwards to digest the things that came out of the ILC meeting. We've been trying to create that sort of similar structure in the gravitational wave community to try to engage the agencies so that they would start to fund things like joint R&D activities that are international. But part of it is that some of the agencies and some of the analogies don't work quite as nicely. For example, in India, also in Japan, where MEXT, which funds CAGRA doesn't like to participate in those kinds of international organizations. So we're struggling a little bit with some of the structures.
Thanks for that comment. I think I would like to say or remind ourselves about what Joe said, that before we get to the funding level discussions, perhaps a discussion at the technology level or the investment in what directions of research we wish to invest in, that discussion could already start. So perhaps that's a good place to start as well.
That's exactly what I was saying to you. How we moving forward with that, it's something that is going to evolve out of the, what's the name of that workshop we have? The Dawn meetings. Dawn is trying to figure out how we start to get this connections together. Yo mentioned that within the LIGO and within Virgo there are these science, instrument science working groups which are getting closer together. The data analysis working groups are already together, and it could naturally spread through the collaborations that way. But I think we want to be open to people who are not already in a collaboration to understand that. Just a minute.
David, I just want to object to this topic. This whole, could we postpone the governance and management until maybe it can be in the LIGO India session or something like that.
Yeah, I'm going to let Yo have his final say, and then I'm going to cut us off because Ajith is going to have a fit if we don't stop talking.
Yeah, so I would like to have the so this adiabatic implementation, make it as simple as possible. So you mentioned new groups. I think that if there is a new group interested in instrumentation or in gravitational wave science, then what they should do is join either LIGO or join Virgo or LIGO India. And then I think they are in contact with the people that probably know how best to put them to work. And I think that would be the way that I start. And I would not like that there would be a new entity. That would be then the group would have to go there. That entity would talk to the funding agencies. I think it's way too confusing. So I would prefer not to have that.
I wanted to just make some positive comment before we finish.
Okay, but use the microphone.
Yeah, it's in line with a bit what Yanbei was saying. I think people may be wondering, why is it important to have this kind of crazy talk go on when we are talking about practical experiments? And I would just remind people that in this field, there's a history since probably the late 1970s where there's an extremely tight collaboration between the people doing the experiments and the theoretical physicists who are helping to think about the project, and not just in the area of calculating waveforms from black holes, but indeed the people who are embedded within these groups who are doing really just pure theoretical physics many, many times that I can remember, even though I wasn't there, but I can remember, there were strong contributions in quantum mechanics and thinking about the detector noise and the operation, which usually took something like 5 to 10 years before it was important. But for example, the topics that Yanbei is talking about now, Alessandra and Yanbei worked on in 2001. And before that was worked on by the theoretical physicists at Moscow State. And here we have it would be a missed opportunity not to emphasize this because we have such a strong team of theoretical physicists in this room. And what you can contribute to the LIGO India project is to help us to think how to solve these problems in a smarter way than what we are doing now. And you'll be surprised, but I bet every one of you has some important skill which will really make the experiment not be so simple, but rather be more clever. So please contribute. Okay, and I'm sorry, but I am going to cut this off so that we can get on to the really important thing for the day, which is the social program to celebrate Bala.